Mission Director.
This is EMD. You have permission to launch.
Proceeding with the count.
L-minus 6 minutes.
MEQ, establish swing arm lock pins pulled.
Roger, in work.
Launch team is Polling is complete and the launch team is given a go for launch. The countdown will resume in approximately 2 minutes from now. At T-minus 4 minutes and counting, the team will enter the terminal count and will begin securing the second stage liquid oxygen tank. At T-minus 332, booster liquid hydrogen and liquid oxygen tank securing is started, which includes closing the propellant fill and drain valves. Also at T-minus 332, vehicle transfer from ground facility power to its own internal battery power will be complete. At T-minus 3 minutes, the vehicle ordnance system will be armed and the booster liquid oxygen and liquid hydrogen propellant tanks are verified to be at flight pressure and flight level. At 2 minutes prior to liftoff, the team will verify that the hydraulic system is pressurized, as well as confirm booster, DCSS, flight termination, and battery voltages. At T-minus 120, the team will begin securing the second stage liquid hydrogen tank. At T-minus 60 seconds, the eastern range readiness is verified. At T-minus 50 seconds, the DCSS liquid hydrogen tank is secured at flight level. A final launch vehicle and spacecraft status check is conducted at T-minus 30 seconds. At T-minus 15 seconds, the ROFEs, or sparklers, are ignited to burn off excess hydrogen at the base of the vehicle.
359.
Second stage lock secure at flight level.
355.
Ground pyros in.
The countdown clock is resumed and we are go for launch at 8:26 p.m. Eastern Time.
.307. .249.
FTS internal.
CBC locks at flight pressure and flight level.
.2 minutes. 159.
Vehicle internal.
Hydraulic press at without.
155.
CBC LH2 at flight pressure and flight level.
140.
FCS launch in.
37.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
120.
LCU's armed.
FCS count start.
T-minus 1 minute.
Box, go.
Rock, report range status.
Range green.
50.
Second stage LH2 secure at flight level.
30.
Status check.
Go Delta.
Code WGS-10.
23.
SRM TVC blowdown.
15.
Profi ignition.
10.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Delta IV rocket carrying the WGS-10 mission for the United States Air Force.
Passing 10 seconds into flight. RSCT chamber pressure looks good. See good chamber pressure across all 4 SRMs. Nice symmetric burn. Now 20 seconds into flight. Continue to see good performance on the RS-68A engine. Now coming up on 30 seconds. 34 seconds into flight. Mach 1 Delta IV is now supersonic. SRM chamber pressure has tailed off from the max pressure as expected. Continue to see good engine performance on the RS-68 engine. Delta is now passing through max Q, maximum dynamic pressure. Now 55 seconds into flight. Continue to see good performance on the RS-68A engine, good performance on all 4 SRMs, nice symmetric burn. Now 1 minute, 5 seconds into flight. About 30 seconds remaining until SRM burnout. Now passing 1 minute, 15 seconds into flight. Continue to see good performance on the main engine. And standing by for SRM burnout shortly. And we have burnout on all 4 SRMs, standing by for jettison. And we have good indication of jettison of all 4 solid rocket motors. Main engine continuing to perform well, chamber pressure looks good. Now passing 1 minute, 50 seconds into flight. Vehicle's gone to closed loop guidance. The Delta IV rocket now weighs just 1/2 of its liftoff weight, burning propellant at a rate of almost 2,000 pounds per second. Now 2 minutes into flight, the second stage ACS system press valve has been opened. System pressure response looks good. And seeing good body rates on the Delta IV as it transitioned to closed loop guidance. Main engine continuing to perform well, engine parameters look good. Now 2 minutes, 18 seconds into flight. Launch vehicle is now 46 miles in altitude, 73 miles downrange distance, traveling at 5,400 miles per hour. Continue to see good performance on the main engine, passing 2 minutes, 35 seconds into flight. And body rates have nulled out now, 2 minutes, 45 seconds in. And the upper stage lock system has begun the boost phase chill down sequence to begin thermal conditioning of the RL-10 engine. Now 2 minutes remaining in the boost phase of flight. And upper stage fuel system has begun boost phase chill down. Standing by for payload fairing jettison. And we have good indication of payload fairing jettison. Approximately 20 seconds remaining until booster begins to throttle down in preparation for BECO, continuing to see good chamber pressure on the RS-68A engine. Now 3 minutes, 40 seconds into flight, standing by for booster throttle down momentarily. And boosters now throttling down in preparation for BECO, standing by for BECO. And we have BECO booster engine cutoff standing by for stage separation. And we have good indication of stage separation. Nozzle extension is deploying. We have pre-start on the RL-10 standing by for ignition. And we have ignition on the RL-10. Chamber pressure looks good. Body rates look good. This is the first burn of today's mission. This first burn will last approximately 15 minutes, 15 seconds. Now passing 4 minutes, 30 seconds into flight. RL-10 chamber pressure continues to look good. Body rates seeing a
This
small
is Delta Mission Control at T plus 4 minutes and 48 seconds. We've just heard Patrick Moore report the successful execution of the early events for tonight's flight, and all systems continue to operate nominally. The Delta IV second stage and WGS satellite are traveling over the Atlantic Ocean in a southeasterly direction away from the coast of Florida. The mission is now in the first of 2 planned RL-10 engine burns. This burn will last approximately 15 minutes. Momentarily, we'll hear from Boeing's Tim Maurer to tell us more about the spacecraft. But first, let's take a look at a message from the Boeing team on what it's been like working on the WGS program.
This satellite is providing this capability that provides for the freedom that we have here.
I know that I'm working on something really important. It helps out the warfighter. It makes sure that all of our troops stay connected. It also allows them to stay connected with their families, which I think is really important.
I hope that the people watching this webcast really understand how many hours and how many people had a hand in shaping this very successful program.
My hardware was responsible for controlling the spacecraft.
So I started as the payload system engineering lead on the program. When the program started out, slowly moved in to become the overall payload IPT lead, and then I became the Block 1 program manager.
So I started out as an attitude control subsystem analyst, and I was moved up to be the platform IPT lead.
When your work is important to the military, our country, and the world, you feel better about what you're doing.
There's a feeling like you're doing something good for the country when you're working on a program like that.
There's a good feeling of helping the military and helping the Department of Defense with something that they have a big need to fulfill.
We're now joined by Boeing's Tim Maurer. Tim, thank you so much for being here.
Thank you, Andrea.
Great. I know I'm really excited to learn more about WGS and what you do specifically. So to go ahead and get started, what I'd like to do first is just get to know a little bit about what you do and your involvement with the WGS program.
Great. So, as you mentioned, I work on the ground system for the WGS spacecraft called the Global SATCOM Configuration Control Element. I've worked on this system over various roles since 2003, very near to the initial WGS contract award in 2001. The Army uses the Global SATCOM Configuration Control Element to control the payload. So right now, I'm an integrated product team lead for the Mitigation and Anti-Jam Enhancement Program, or MAGE. MAGE is making changes to the WGS ground system to provide additional enhancements for mitigation and anti-jam for new capabilities for the WGS spacecraft. So as an integrated product team lead, it is my responsibility to ensure that the team focuses on the right priorities to meet our schedule and deliverables. I also work with our customer, the United States Air Force, to ensure that they're fully involved in the process and are satisfied with our approach and progress.
Oh, great. Quite a bit of integration that you do. I can see that. And it's really important that you meet those schedule milestones. So I can really appreciate that. Obviously, it's very important to get those secure communications out. So.
Absolutely.
Great. So now that we know a little bit about what you do and your involvement in the WGS program, I want to learn more about WGS itself. So I'm going to dive into a couple of questions about that.
Certainly.
Sounds great. So how does Boeing design and build secure communications features into the satellite?
So first it starts with the mission. In this case, providing secure, high-bandwidth communications for warfighters, ground stations, and vehicles worldwide 24/7. From there, capabilities and requirements are defined and designs created. Next, hardware is built and integrated in our factory back in California, where we test our satellites in environments that exceed what we predict will occur in space. Once that is done, I guess really the question is more not how we do it, but why we do it. As a Boeing employee, this is really more than just a job to me. The products we build serve a greater purpose to protect not only every American, but also our allies. When I walk into work, I know that I'm designing and building the tools that will protect liberty and freedom throughout the world.
That's such an amazing and inspiring message that you just put out there. I think that, you know, in the aerospace industry, especially when we're talking about national security and bringing home our soldiers safe from war, there's no better reason to go to work and do a good job every single day. So thank you for all of the effort that you've done to, you know, work on these WGS satellites and make them be very effective out there, especially on the warfield.
Thank you. It's an absolute honor for me, and I know the rest of the team.
Great. All right, so you did mention a little bit about building and testing. Can you expand on that a little bit?
So most of the satellites that Boeing builds, both government and commercial, come out of our factory back in El Segundo, California. The things that we do to test basically simulate the environment we expect the satellite to be in. Everything from the launch environment, which we just saw with the vibrations and noise, to the space environment with things like radiation and temperature extremes. So in testing, we really have to stress the satellite to put it through its paces that we predict it will be in. So the satellite's payload really is what performs the mission of the satellite. I guess one of our, basically at our factory, we do everything from design, development, manufacturing, integration, and test. So once everything is complete with the integration and test and we've stress tested it, we next move on to making sure that it's ready for launch. Once it's ready for launch, basically it is containerized and shipped to the launch site. So for WGS-10, for example, it moved from our factory to the LAX airport, boarded a Boeing-built C-17 aircraft, and flew here to Florida. So once at its launch destination, it goes through a few more tests before it's finally encapsulated and prepped for launch.
So there's quite a bit of testing that goes on throughout the entire process.
Absolutely.
Amazing, and it's really nice that you have all of those integrated facilities at Boeing. So not only do you do the testing and the development, but you also do transportation and follow the satellite through the entire process.
Full process, yeah.
Yes, and you know, I always think test like you fly. We love to say that all the time. So like you said, we saw a really harsh environment.
Yes.
We felt it here. We literally felt the floor move.
Yep.
So it's amazing that these satellites can handle those type of environments.
Definitely.
All right, so we've talked a lot about Boeing and how they build the satellites and things like that, but there's much more than just building. We're going to launch today, and then after the launch, what's next? What does Boeing do to support the WGS constellation?
So WGS is controlled by two different systems on the ground. One is primarily responsible for the platform, or flying the satellite. This is keeping it in its designated orbital slot and pointed correctly, as well as changing orbital slots if necessary. The other system is responsible for configuration and monitoring of the payload, so pointing antennas, configuring routes through the channelizer to connect uplinks and downlinks, and a few other configuration parameters. So the payload control system itself was developed by Boeing in parallel with the construction of the WGS satellites. That system is deployed at various sites around the world, and it is what's used to collectively manage the configuration of the WGS fleet. In addition to developing the payload control system, Boeing also supports, through their sustainment services, the day-to-day payload and platform operations of the WGS constellation. So I mentioned MAGE earlier. This is the ground-based anti-jam enhancement that will use existing WGS capabilities to geolocate where interference is coming from and then shape beams to mitigate that interference. So in addition to MAGE, to further improve the security of the communications that our service members use every day, Boeing is working with the Air Force to roll out another ground system in the early 2020s that will enhance protected tactical communications over WGS. So this system is called the Protected Tactical Enterprise Service, or PTES. PTES is a global military satellite communications ground system. PTES will use WGS satellites to allow service members to use the Protected Tactical Waveform, which is one of the U.S. Department of Defense's secure anti-jam waveforms. So we are proud to partner with the Air Force because we know the work that we have done on the WGS satellites really play into a larger system that ensure critical communications for our soldiers and service members so that they are never alone and they always have the information they need to execute their mission.
It's incredible that you say that, and like I said before in a previous question, it really gives you no better job satisfaction knowing that you're able to do things like that. But bringing home people safe and being able to always have that constant communication, I don't think there's anything quite like it.
I absolutely agree.
Yeah, so thank you for that.
Sure.
All right, so I just have one more question for you.
Okay.
Boeing has a robust history, as you know, of building satellites, about 50 years or so between commercial and military type satellites. What is it about WGS that makes it unique?
So WGS is a really interesting looking satellite. One of the most distinguishable features on the satellite are the solar panels. So WGS satellites employ highly efficient space solar cells made by Spectrolab, which is a Boeing subsidiary in California. So on the sides of the satellite are the Ka band antennas. There's also two large polygons on the top, which are the X-band phased array antennas. These polygons hold many different antennas, or horns as we say, and we can phase those antennas together to create beams that we can then point to create our communications. We can also shape those to enable the anti-jam capability. Deep in the cavity of the satellite, behind the radiator panels, is our Generation 6 channelizer. You can think of a channelizer as a computerized switchboard in space that would connect a ship to a commander in the field, for example. So this channelizer, which was also included on WGS-8 and 9, nearly doubles the available bandwidth as compared to earlier WGS satellites.
Wow. Wow, that's incredible.
It really is.
So WGS is very unique, is the answer to that question. Great. So we've learned a lot today about WGS, and you are very knowledgeable on the systems, and I know we very much appreciate your time, but we have another video from Boeing where we're going to go into a little bit more detail on WGS. So let's go ahead and take a look.
Okay.
Virtually every military mission relies on satellite communications. From data gathered by UAVs to teleconferencing between military leaders, WGS is the backbone of our military's ability to communicate. One satellite by itself can't service the entire globe, so it's really important to have an entire network of satellites to make sure that we have full coverage. WGS is the satellite network used by the military and our allies to communicate across the world, anytime, anywhere. We want to protect the satellite as much as we can, So WGS is going through a fleet-wide upgrade right now by uploading new software and modifying the ground segment to allow continuous communications that aren't interfered with. One of the major things that the military has been looking into is how to make satellites more resilient to jamming. Sources of jamming can range from an adversary that's trying to affect your communications path to someone who is accidentally in that bandwidth. One of the enabling technologies for anti-jam capabilities is the use of phased array antennas. By adjusting the power and timing of each of the antenna elements, we're able to create a shapeable beam to avoid the jammer that allows for warfighters to stay connected wherever they're located. When you take into account satellites that allow upgrades through software and the ability to provide anti-jam protection, it all allows us to provide a more resilient system that the military can count on.
And we have MECO, main engine cutoff. Vehicle body rates are recovering nicely from the shutdown transients. And we have begun the thruster activity to correct the body rate dispersions as expected.
As you just heard, we just saw the successful execution of MECO 1. Thank you so much for coming and joining us today and telling us all about WGS. It was great to have you.
Thank you, Andrew. It was my pleasure.
Awesome. Thank you.
Second stage is now turning to the MES 2 attitude as expected. Now 21 minutes.
All right. I am now joined by Sam Wiley. Sam, thank you so much for being here.
Thanks so much for having me. Glad to be here.
Great. I know we have a couple of questions to ask you about WGS, so why don't we go ahead and get started?
Okay, let's do it.
All right. Why don't you start off this interview by telling me a little bit about WGS?
Okay. WGS provides flexible, high-capacity tactical communications to the Air Force, Army, Navy, Marines, Coast Guard, and our international partners. WGS is one program of 6 divisions at the MILSATCOM Systems Directorate at SMC in Los Angeles. The MILSATCOM Directorate develops, acquires, deploys, and sustains space-enabled, war-winning global communications.
It's amazing that we've been able to partner with our allies in such a meaningful way. Can you tell us, you mentioned a little bit about satellite communications. Can you expand on that?
Sure. Generally speaking, radio frequency or RF communications require line of sight to transmit a signal between users. When those two users are over the horizon from one another, a communication satellite must relay that signal. WGS has extremely advanced and innovative technology that enables these communications at extremely high speeds.
Great. So to kind of build on that, can you give us some specific details about WGS-10?
Absolutely. Each and every WGS satellite has more bandwidth and capability than the entire legacy constellation that came before it. Yeah. WGS is the only military satellite communication system that provides simultaneous communications, X-band and Ka-band communications with cross-banding, meaning that 2 users who are on different communication bands can still seamlessly communicate. WGS can also point communication beams and can reposition satellites on orbit, providing unparalleled flexibility to our warfighters and international partners with any contingency that they may have to execute.
Amazing.
With its ground equipment and software updates, WGS has shapeable beams, which allows the satellite to outline a coverage area that eliminates jammer effectiveness. The speed, reliability, and effectiveness of the WGS constellation allow U.S. and international partners the ability to efficiently coordinate in all mission areas, including air, land, and naval warfare.
Wow, that's great. So, as you know, we're currently in the process of launching WGS-10.
Yep.
I know you got to go up to the roof and see it, so that's pretty exciting.
It was awesome to watch
Yeah,
in person.
I bet. Can you just tell us what the plan is for WGS after today's launch?
Absolutely. So prior to operational use, the satellite will be positioned in the geo belt orbit, where it will undergo a series of rigorous tests to ensure that all systems are performing to spec. Once payload performance is validated, the satellite will transition to its operational slot, where our warfighters and international partners will be able to use it.
That's great. So our viewers may not know this, but this is WGS-10 is the last satellite of the Block 2 follow-on contract, which was able to provide much faster communications than previous satellites. What do you think's been the key to all of this success?
So there are multiple keys. The satellites on the Block 2 follow-on contract, WGS-7 to 10, were early forerunners in the streamlining processes, mimicking those used in the commercial industry. On average, delivery times were reduced by 10 months per vehicle without additional cost. These principles will continue to be used for the proposed WGS-11 contract and are vital to the SMC 2.0 initiative, which will make SMC as a whole operate faster, and it will increase or improve the agility of U.S. Air Force space acquisitions altogether.
Incredible. What an incredible satellite and what an incredible day we've seen so far.
Yeah, it's been amazing.
All right, so that's all the questions I have for you right now, but you and I have some really fun stuff to do in just a little bit. So why don't you stick around? Right before stage separation, we're going to go ahead and answer those Twitter questions and get some winners. Get some prizes.
I'd love to get some of those prizes.
I know, I want some of those prizes too. All right, for now, we'll get back to launch and we'll see you in just a bit. We have about 4 minutes until main engine start 2. While we wait, let's take a look at my conversation with Brett Bushy, ULA trajectory engineer who I had the opportunity to speak with prior to MST roll. Hi, I'm here today at Space Launch Complex 37 with an engineer from ULA, Brett. Brett, thanks for being here.
Thanks for having me.
As you can see, we're pretty excited because you can see the Delta IV rocket right behind us, and it's a beautiful day. Brett, why don't you start off by telling us about what you do at ULA?
So I currently serve as the Flight Design Certified Responsible Engineer. So I serve as the focal point between the various launch vehicle, hardware and analysis teams and the spacecraft customer as we go through the integration process to come up with a mission design that satisfies not only the spacecraft requirements but also the launch vehicle system and subsystem level requirements. I first started as a trajectory engineer about 29 years ago and progressed through the ranks to actually get this position, and I've been lucky enough to work with a great team of engineers.
What's been your involvement with the WGS program as a whole?
So our group basically takes the inputs from all the various launch vehicle groups and integrates those all into a cohesive trajectory that meets not only the internal launch vehicle requirements but also the spacecraft requirements. So that we go through several different trajectory cycles where we refine the design and improve it, and we basically our team comes out with a final product, and then my job is to review that final product before it goes out the door and sign off on that trajectory design such that that's what gets loaded onto the vehicle and that's what we end up flying. So our group also integrates with a lot of various different organizations to actually make this all happen. So not only do we integrate and interface with the spacecraft customer, we also integrate and interface with the 45th Space Wing to get their approval that our flight plan is acceptable. So it's been great that I've been able to work with a great team of engineers who I've actually seen on a lot of these broadcasts over the years.
In tonight's mission profile, we saw a brief overview of what today's trajectory will look like. Can you expand on that a little bit?
So as you've seen on the broadcast, this mission is typical for an Eastern Range mission where we fly due east when we come off the pad. So we do about a 4-minute burn of the booster, and then we follow that up with about a 15-minute burn of the upper stage, and then go into about a 10-minute park orbit coast. And then we follow that up with a 3-minute burn of the upper stage, and then 4 minutes later we separate the spacecraft into a supersynchronous transfer orbit, which is a little bit different than what a typical geosynchronous transfer orbit is, in that we put it into a higher apogee altitude than what geosynchronous altitude would normally be. And the reason we do this is that actually helps the spacecraft in their propellant utilization and tries to minimize what they actually need to get to their final orbit.
As you know, ULA has launched the previous 9 WGS satellites. Can you provide us with more detail on that history?
So we started about 11 years ago launching the first WGS spacecraft. We launched that on an Atlas V vehicle. In fact, we launched the first 2 WGS satellites on Atlas V vehicles. And WGS was actually designed to be a dual integrated spacecraft, so it can launch on both an Atlas V and a Delta IV. So the last 7 launches will have been on Delta IV launch vehicles. So starting with WGS-3, we launched on a Delta medium 5-4 vehicle configuration. As the Delta IV vehicle evolved and we upgraded the engines, we went back and redesigned the trajectory several different times as we've gone through the various WGS launches, with the last WGS-10 launch culminating in our common avionics upgrades on the Delta IV vehicle.
Well, Brett, thank you so much for joining us today. I know I learned a lot.
Thanks for having me.
Let's get back to the launch.
RL-10 engine operating parameters continue to look good, now passing 30 minutes, 7 seconds into flight.
This is Delta Mission Control at T plus 30 minutes, 13 seconds. As just reported, the RL-10 engine has been restarted. Our next event, MECO 2, will occur soon.
RL-10 chamber pressure, LOX and LH2 inlet pressures all look good. And seeing good body rates throughout the second burn. And seeing some periodic thruster activity as expected. Seeing the ACS line temperatures are staying very close to bottle temperatures. Now 2 minutes remaining in the burn. Now passing 31 minutes into flight. About 1.5 minutes remaining in the burn. RL-10 engine operating parameters continue to look good, seeing good stable body rates throughout the second burn, and seeing consistent values on the LOX and LH2 tank pressures. And about 1 minute remaining until main engine cutoff. Engine continuing to perform well throughout the second burn. Thrust chamber pressure maintaining a good value.
We are now approaching main engine cutoff 2. Let's listen in.
Now standing by in approximately 10 seconds for engine cutoff. And we have MECO, main engine cutoff. Body rates are damping out nicely from the cutoff transients, seeing thruster activity to recover.
We've just heard confirmation of the successful cutoff of the RL-10 engine. The mission is now in a 4-minute coast phase, flying above Western Africa. Separation will occur over the southwest coast of Madagascar, approximately 40 degrees east longitude and 18 degrees south latitude. All right, now let's go ahead and welcome back Sam. Sam, thanks for being here again.
All right.
I think we have a very exciting thing. We're going to announce our Twitter winners.
All right, let's do it. Let's get started.
All right, let's go ahead. Let's jump right into it. Question number 1 was, when was Wideband Global SATCOM 1 launched and on what rocket?
And the answer is WGS-10 was launched by an Atlas V 421 rocket on October 10th, 2007. Congratulations to @Close to Space.
Yeah, you get a prize. Woohoo! Okay, question 2. How many WGS satellites launched on Atlas V rockets? How many WGS satellites launched on Delta IV rockets?
And the answer is 2 satellites, WGS-1 and WGS-2 launched on Atlas V rockets, and 7, now 8, launched on Delta IV rockets. Congratulations to @Tadastaraska.
Yeah, congrats. Okay, next question. Who is the exclusive launch service provider for Wideband Global SATCOM satellite constellation? If people get this wrong, that would be embarrassing.
Very. And the answer is United Launch Alliance. Congratulations to @SkipLacombe or LAcombe. Congrats.
All right, our final question. One more winner. How many allied nations collaborated with the U.S. military on WGS-9?
And the answer is 5 nations partnered with the U.S. military on WGS-9. Canada, Denmark, the Netherlands, Luxembourg, and New Zealand. Congratulations to @HighFlightPhotos. Congrats to all our winners.
Congrats, you guys. I hope your prize is amazing. All right, we're really close to spacecraft separation now. Let's go ahead and get back to the flight.
Apogee, perigee, and inclination all look very close to pre-flight predictions. Now just 1 minute remaining until spacecraft separation. Vehicle body rates remaining close to null as the vehicle is staying in its desired spacecraft separation attitude. And seeing settling thruster activity as the vehicle prepares for spacecraft sep. Now 30 seconds remaining until separation. Standing by for spacecraft sep. And we have good indication of spacecraft separation.
Sam, we just heard evidence of successful stage separation with WGS-10 satellite. Congratulations.
Thank you, Andrea. This is another important milestone for our warfighters, our nation, and our allies. Go wideband and hang 10.
Great indication there. I'd also like to thank Patrick Moore for providing us with launch commentary today. If you want to learn more about today's launch and United Launch Alliance, please visit our website, ulalaunch.com. You can also visit us on Facebook and Twitter. We'll leave you now with another look at liftoff of the Delta IV rocket carrying the Air Force's 10th WGS satellite. I'm Andrea Lenhoff. On behalf of the entire launch team, thank you for joining us and have a great night. 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Delta IV rocket carrying the WGS-10 mission for the United States Air Force.
Passing 10 seconds into flight. RSPD chamber pressure looks good. Good chamber pressure. Press RM's nice to measure. 20 seconds. Continuing to see good performance on the RS-68A engine. Now coming up on 30 seconds. 34 seconds into flight. Mach 1 Delta 4 is now supersonic. SRM chamber pressure has tailed off from the max pressure as expected. Continue to see good engine performance on the RS-68 engine. Delta is now passing through max Q, maximum dynamic pressure.